Let us look at the geomagnetic polarity time scale. Here it is presented. From top there is Brunes, Matuyama, Gauss and Gilbert. As per the latest use of the terminology, they are called as Cron, below which lies Cron 5, then Cron 6 and then Cron 7. Brunes is Cron 1, Matuyama is Cron 2, Gauss, interesting, is still C2, and Gilbert, now we are using C3. Now in Cron 5 also we are using C3, in Cron 6 we are also using C3, and in Cron 7 we are using the term C4. So there is a disparity. If we write a number after C and the Cron number, they need not match. Note that these two numbers do not match here, whereas here if we are thinking like Brunes is Cron 1, then 1 is matching. When we say Cron 5, Cron 6 and Cron 7 and the corresponding C numbers, these numbers do not match with 5, 6 and 7. If we go down from Brunes, we find a reverse polarity given by the white box and then a normal polarity given by C. So, this one is given by C1R dot 1N. Here N stands for the normal polarity, is called as the Jaramillo subcron. It is a division of the cron, therefore the term subcron is used. It indicates normal polarity at around 1 million year and it is a part of Matuyama. We see that C1R dot 1N is a part of Matuyama. Given that the duration is much smaller when compared to the history of the earth of 4.6 billion years. Matuyama started at 2.58 million years back. The Gauss started at Pliocene time. If we compare this GPTS with the magnetic anomalies in the sea floor, consider a mid-oceanic ridge, and here is the uprising magma and the older igneous rock is pushed at both the sides due to the influx of the new batches of lava. Here geoscientists have been able to locate C1 Cron 1, which is the Brunes. As one goes from Brunes and away from the ridge, for example from this Brunes and away from the ridge, we encounter a reverse polarity zone. This reverse polarity zone can be correlated with the GPTS by this portion. Note here APTS stands for the astronomical polarity time scale. What is that? Where the reversal is accurately dated. So, the dates can be correlated in this way. After this white box comes this black box, thin one, which is here. As one moves from this thin black box towards this white domain, well, this is that white domain, and after that what comes? 2 is found, and indeed here we can correlate C2N. So, C2 up to C2N we have been able to correlate. This C2 is the Olduvai subcron, and this Olduvai subcron comes within the Matuyama cron. As one goes away from 2, I mean away from the ridge axis, that means in this direction one comes across 2A, which is called Gauss cron. Gauss is over here, and as I told you, we are dealing with a cron, and in the Gauss cron here what do we see? There are 3 black zones, thick one, thin one and thick one. So, here also we are getting 3 black zones, 1, 2 and 3, and all of them are 2A. So, the Gauss cron has been shown. In this way one can link the magnetic anomaly and the GPTS or the APTS. If the findings near the mid-oceanic ridge is projected as a single rectangle, then this is the portion of the Brunes cron, after which lies the C1R 1N, C1R dot 1N. Then comes the black domain, which is the Jaramillo subchron. Then comes this white region, which is comparable with this region, and similarly you can correlate this rectangle with the APTS. One way of presenting this information is given here. Here cron 1 is presented in this way. Here is a Jaramillo. Here C2 is presented. This represents C2A, and here is C3, and so on so forth. Almost a similar thing is presented here, but in this diagram we were crossing 1 million year back, 2 million year back, and maybe this is 2.8 or even 3 million year back. The next figure shows up to clearly 3.3 million year back event, from 0 to 3.3 million year, and the Brunès normal polarity chron, the Mattuyama reverse polarity chron, and the Gauss normal polarity chron are plotted. Note that in the Brunès normal polarity chron, as per this diagram, there is no reverse polarity inside, whereas in the Mattuyama reverse polarity chron there are few normal polarity chrons, and in case of the Gauss normal polarity chron there are thicker normal polarity zone and there are thinner reverse polarity zones. This diagram is taken from the 2014 publication, and by 2014 it was clear that the principal polarity zones names now in use are well established names such as the Brunès, Mattuyama, Gauss and Gilbert, which are used for the most recent 5 million years of Earth history. The Brunès, Mattuyama, Gauss and Gilbert together, the most recent 5 million years of history is covered, and in this diagram this is 5 million year. So, if I extend it, in fact older than 5 million year also the Gilbert chron persists, but 6 million year onward actually we are finding chron 5, 6, 7. Historically these units Brunès, Mattuyama, Gauss and Gilbert were called as epochs, but then the terminology changed and we use the term chron, which was also used here. Chron was used, and any division of chron will be called as subchrons. For example, Jaramillo, Olduvai and reunion. The other usage of term can be the polarity subzone, in case we are dealing with rocks exactly, or in case we are dealing with time, subchron will be a good term. I have shown you different ways of nomenclature of the magnetic normal polarity and reverse polarity. Here are two more examples. One is from the book published in 2009, another is an older publication of 1989. In this diagram, last 10 million years of information is presented, whereas in this diagram, this is 22, so maybe last 24 million years of information has been presented. If we have to choose the one, we should always go for the latest publication. So, if you find any publication of 2025 in authentic journal on geomagnetic polarity time scale, we can go for that. Brunès, Mattuyama, Gauss and Gilbert can be seen. Brunès, Mattuyama, Gauss and Gilbert. Then crons 5, 6, 7, 8, 9, 10, 11 have gone, which are shown here. sea floor anomaly numbers are matching 1 with 1, 2 with 2 and 3 with 2a. So, what is the chron number 3, which is Gauss, is actually in sea floor anomaly is 2a. Let us see, here is the 2a Gauss and it is not 3, which I already explained. Here is 2a. So, here is a Gauss and it is not 3. Then Gilbert is chron number 4, but the sea floor anomaly number is 3, and you can see that the difference starts. So, up to here the sea floor anomaly numbers assigned and the magnetic polarity are the same, but the difference arises here. For example, when it is chron number 11, in the sea floor anomaly it is just 5. Corresponding chron numbers are stated, and Another way of nomenclature in terms of S has been shown. Note that bruness is entirely normal polarity given by the black box, whereas in case of Matsuyama it is not so. Gauss is mostly normal magnetic polarity given by mostly the black rectangles, whereas in Gilbert there are several fluctuations of normal and reverse polarity at quicker intervals. A more recent version of the magnetic polarity time scale, right from 24 million year up to the present, is here, adopted in the 2023 textbook of stratigraphy, where the numbering has changed 1, 2, 2a, 3, 3a, 3b, then 4 and 4a, then 5 and 5a, followed by 5a, 5ab, ac, ad, then 5bc, 5d, 5e, 6, 6a, 6aa, 6b and 6c. We note that 5a and 5aa represent different parts of the magnetic polarity time scale. Similarly, here 6 and 6a constitute different parts of the polarity zone. 6 is here and 6a is here, and then 6aa is also different from 6a. Here is the 6aa. So, this is a more recent version. One needs to keep on watching the research papers, where if any changes take place with time on the way of writing and any updates. Before you started watching this magnetostratigraphy lecture, I have already talked about the lithostratigraphy and biostratigraphy in the NPTEL. Here is a simple figure stating that the lithostratigraphic approach, the biostratigraphic approach and the magnetostratigraphic approach can be used to combinedly correlate different columns. Here is the global magnetic polarity scale, and there are some local columns created A, B, C, D, E and F, and consider that a marker bed has been identified in this place, can be a volcanic ash bed and is shown by this dotted region. Also consider that there has been a biostratigraphic marker, looks like a gastropod over here, found in these three places, where there is entirely black region, which means that this is entirely the normal polarity zone. Now, how we will correlate? This biozone gives us confidence to link these black regions in this way. We do not know whether below this writing C the black zone continues, so we do not know the bottom of this normal polarity zone, of this normal polarity zone. Therefore, we have not drawn the bottom line connecting these two. For example, if I join these two, there is no guarantee. Suppose the black zone has continued here, then it would have gone like this. Same problem, I cannot join this point with this point, and even in this case I do not know whether the black rectangle demarcating the normal polarity actually goes down. So, is this the right correlation, or is that the right correlation, or is that the right correlation, is not clear. Now, immediately above this normal polarity zone there is a reverse polarity zone that we can join. So, this gives a much more confident correlation that these normal polarity zones can correlate, over which lies again normal polarity zone. So, they have been joined. A line has been drawn joining the marker units. So, this line is a lithostratigraphic correlation, whereas joining this line is a biostratigraphic correlation, and when we join the other dashed lines such as this and so many other lines, those are the magnetostratigraphic correlation. So, how to proceed? Basically, the biostratigraphic correlation and the lithostratigraphic correlation to be first done, then it has to be followed by the magnetostratigraphic correlation. Just like the biostratigraphic correlation with index fossil, if there were absolute dates available, then the correlation can be most confident. For the reason we have not joined this point with that point or this point with that point, same argument works that I did not correlate this point with that point or this point with that point, because I do not know whether it continues further and how far it continues. So, this was avoided. For the same reason, this point has not been correlated and these portions remain uncorrelated. Here also is a zone of no correlation being done. There are actually two magnetic scales. One is the geomagnetic polarity time scale GPTS, the other one is called the generalized magnetostratigraphic scale GMSS, and ideally there should be a single magnetic scale, but anyway these two are there. The tendency of the stratigrapher is to link the geological time scale, already I have discussed in the NPTEL lecture, mechanically with the absolute dating and geomagnetic reversals. Now, this is not always possible and this leads to problems. I will be demonstrating also that biostratigraphic correlation can go diachronous, and this along with the attempt to link with geomagnetic reversals, magnetic scales and absolute dating sometimes create trouble. I refer there are two scales GPTS and GMMS and they sometimes do not match. So, there is a disparity and research goes on to make them to correlate these two as far as possible. Let us see what are the differences. We have taken a GMSS and GPTS, and this GMSS goes up to 78 million year till the present 0 million year, whereas here at least from here it is 80 million year to the 0 million year. Now, when this correlation has been made by someone and if I compare with the absolute age, what do I observe? This is at 72.1 million year, whereas here it has linked with almost 73 million year. This creates a trouble. This line actually demarcates the contact between the white rectangle and the black rectangle, that means the contact between the reverse polarity zone at the bottom and the normal polarity zone at the top. Here what happens? The bottom is a normal polarity zone and the top is a reverse polarity zone. So, these are the problems. Again, let us take another case of a GMSS and GPTS. Here we are looking at 60 million year till the let us say 53 million year, and here we are dealing with 61.5 million year up to 53 million year, and here a correlation has been made. This correlation for the GMSS shows that at the bottom is a normal polarity zone and the top is a reverse polarity zone, whereas here we observe at the bottom is a reverse polarity zone and the top is a normal polarity zone. So, here is a problem. That means maybe either this is wrong or that is wrong or both of them wrong. Some corrections are required. Take another example, 426 million year up to 424 million year, and here in the GPTS we are dealing with 434 million year up to 426 million year. These are the correlations, and here we observe that this correlation, here this line passes through normal polarity zone, whereas its equivalent passes through a transition zone and a normal polarity zone. How is it possible? The Earth's polarity switch affects the rock synchronously, but how it is happening? This is the question. Is there a mistake in dating? Is there a mistake in correlation, or is there a mistake in GMSS, or is there a mistake in GPTS? Similarly, this you can look at where is the problem. Let us look at a part of the Cretaceous time scale where the M sequence is presented here and here is the C sequence. The bottommost of C sequence is here and the topmost portions of M sequence is there, and the ammonoids have been linked, Tethyan ammonoids and the boreal ammonoids. Now, with M0R, the kind of Tethyan ammonoid cannot be linked synchronously with the boreal ammonoid, rather a diachronous relation has been established. So, the biostratigraphy itself can sometimes give a diachronous relation. So, linking a diachronous relationship with the absolute time scale, putting them side by side and bringing a magnetostratigraphic scale in between may not be satisfactory, and for that reason one needs to keep on doing research in stratigraphic scales fine tuning. We will initiate chemostratigraphy. The subject has attention in last 40 years or so. Books older than 1970, you may not find a dedicated chapter on chemostratigraphy, and discussions will be scattered here and there. The simple definition of chemostratigraphy can be, it's a stratigraphic approach where the chemical techniques involving the applications of inorganic geochemical data is handled. We are dealing with stable isotopes in handling chemostratigraphy. The use of unstable isotopes will be discussed in the geochronology part of stratigraphy. The subject chemostratigraphy was pioneered in 1970s. It does not mean that before 1970 chemical analysis of rocks were not done, but the subject came into prominence in 1970s and papers started coming in 1980s. It became popular in hydrocarbon reservoir correlations, finer correlations in the last 30 years or so. How the chemostratigraphic work became important, Cold War and subsequent search for the energy resources pushed the chemostratigraphic studies in detail. It is interesting to note that at present in 2025 also there is a tremendous search for the energy resources, and in fact different new chemical techniques are attempted in the geochemical lab to check whether chemostratigraphic correlations can be made. The chemical analysis can work on rocks of any type. That means it can be sedimentary, igneous or metamorphic of any age, millions of years old or billions of years old, or recent rock few thousands of years old, or recent sediments. The rocks that we will handle can deposit in any environment. It can be deep sea marine environment, it can be shallow marine environment, it can be aeolian environment, it can be lake deposit, it can be an old rock that indicates an anoxic environment in the past. Drilling might be done to sample. If we are interested in subsurface rocks, then cores become important and the cuttings are used to analyze for geochemistry. Field outcrops, if required, can be hammered and can be studied for chemostratigraphy. The advantage of chemostratigraphy is that here we can attain higher resolution of correlation. If we look at the definition of chemostratigraphy as per the International Stratigraphic Code, study of temporal and spatial geochemical variability of rocks with a view to establish mappable rock units, but what is the scale of such map is not said. Defined in terms of unique geochemical composition, isotope ratios and elemental or elemental oxide ratios. This says everything. Geochemical composition, element concentration, the isotope ratios, the oxides and their ratios, we will see them, or combination of these techniques. Now, the elemental and isotope chemostratigraphies are used as tracers for glacial events, build-up of volcanic gases, role of volcanism in mass extinction, in salinity variation, redox state of the ocean in the past and the atmosphere, and to study the provenance, the source from which the sediments came, and there are also other applications. That is why I wrote GH, etc. So, the chemical analysis of rock is indispensable not only for correlation chemostratigraphically, but also to understand the paleo environment. It becomes important. That is the reason that the geochemistry is a very active field in geoscience. While studying chemostratigraphy of the sedimentary rocks, we should remember that the appearance of new class type in the sediment succession can indicate the time when the new source area of lithology was exposed and eroded. Suppose in a basin we are finding an assemblage A plus B, and then over that we find A plus B plus C, a new class type. Then in that case, this top layer indicates a source rock where C was present, and then that has joined. This is the meaning of this sentence. When we do the bulk chemical analysis of the rock, that means it is the analysis of all the minerals present from a representative portion of the rock, not just specific minerals, then this data can become difficult to interpret. The reason is that grain size can become an issue, and more importantly, the diagenetic alterations can become severe. The same source S has given rise to deposition D1 and D2. Now, in D2, the diagenetic alteration is too much or different from D1, then by geochemical analysis D1 and D2 might be difficult to correlate, and this becomes a problem of the bulk chemical analysis of rocks. Just like diagenetic alteration, late phase fluid movements, depending on what kind of fluid is coming in contact with D1 and D2, there can be chemical changes, and that can preclude a correlation between D1 and D2 even though they can be coevally deposited.